Welcome. We are familiar with the general concept of a function. A function can be seen as a machine that transforms an input to an output. For example, the function square takes the input 3 to the output 3 squared equals 9. Let's review the terminology related to functions. Recall that the set of possible inputs is called the domain of the function, whereas the outputs should be elements of the codomain. In the example square, both the domain and the codomain are equal to the set of real numbers. To emphasize this, we write f from R to R. If we once again take our input 3, the corresponding output 9 is called the image of 3. We can say 3 has image 9 or 3 is mapped to 9. Notice that not all elements of the codomain are reached as images by the function square. For example, the element -1 is not reached by the function square, since a square can never be negative. The set of all actual outcomes of a function is called its range. In our example, the range of f is the half open interval from 0 till infinity. Notice that the range is a subset of the codomain, but as in our example, it does not have to be the entire codomain. More formally, a function f from a to b is a rule that assigns to each element x in the set A a unique element f of x in the set B. The set of all possible input values is called the domain. The set of output B is called the codomain. The range R of the function f from A to B is the set of all possible values of f of x as x varies throughout the domain A. Or, more compactly, the range is a subset of the codomain R, which is a subset of B. In principle, the domain and the codomain can be any set you can think of. However, in this course, domains, codomains, and ranges of functions we consider will always be sets of real numbers. In the previous lecture, we have seen that a useful way to visualize a function is via its graph. If f of x is a function with domain A, then its graph is the set of all possible points xy in the coordinate plane such that y is equal to f of x and x is in the domain. In the example on the screen, the domain is given by the red interval on the x-axis and the range is given by the orange interval on the y-axis. Sometimes an explicit formula is given for a function f of x, but without specifying explicitly its domain. In such cases, we take as domain the set of all values x for which the value f of x exists. In other words, for which f of x is a real number. This set is usually called the maximal domain of the function, and sometimes also just the domain of the function. It is often easy to determine the maximal domain of a function f of x, given by an explicit formula. We just have to exclude those values of x that would result in dividing by 0, or taking square roots of negative numbers or logarithms of non-positive numbers. For example, the function f of x is equal to 1 over x squared has as maximal domain the set of all non-zero real numbers R excluding 0, because 1 over x squared is defined for all non-zero numbers x. The maximal domain can also be seen as the union of the open interval minus infinity till 0 and 0 till plus infinity. What is the maximal domain of the function f of x is equal to the natural logarithm of x plus 1. The logarithm function is only defined for positive arguments. Therefore, the function f has as maximal domain the set of real numbers x that satisfy x plus 1 is larger than 0. The maximal domain is therefore given by the open interval -1 till plus infinity. Let us consider a more difficult example given by the rational function f of x on the screen. The numerator is defined for all real numbers x and yields no problems. Since one is not allowed to divide by 0, we need to exclude all real numbers x for which the denominator x squared minus 4 equals 0. We therefore have to exclude x is 2 and x is minus 2. So the maximal domain of the rational function consists of all real numbers except plus or minus 2. Or, in interval notation, the union of the open intervals minus infinity till minus 2 till plus 2, and plus 2 till plus infinity. Sometimes it is necessary to restrict the domain of the maximal function. For example, you know that the formula for the area of a circle with radius r is given by a of r is pi times r squared. As the function of the variable r, the function a of r is defined for all real numbers r. So the maximal domain of a of r is equal to the set of all real numbers r. But negative radii, of course, don't make sense. So a more natural choice would be to take as the domain of the function a of r the set of all non-negative real numbers, that is, the interval from 0 till infinity.